with the question. The question was that if you look at this diagram, especially here, the middle one, lymphocytes, what they're showing is with various doses, 1 microgram, I wish this thing stopped bringing up this 1 microgram, 10 microgram, 20 microgram, and 30 microgram. Then if you see 3, that is before the dose, the empty rounded circle, day 2, and then day 8. So the way, let me draw it because it won't let me hover my mouse over it. So they have a, let's say one person, these are 11 people, but let's say one person receives a dose, X amount. So what they do is they take their blood before and they count the lymphocytes, and they have a number there, and they say, well, the number of lymphocytes per nanoliter of the blood are X, let's say 10. I'm just making up a number. You can actually see the numbers here, 1, 2, 3, 4 counts per nanoliter. So let's use any one of them. Let's say this one here, 2.2. So let's say 2.2 before the vaccine. Then the vaccine dose is given. So this 2.21 is 10 microgram. So when that dose is given in 2 days, it dropped, the lymphocyte count dropped to, let's say, 1.8. 1.8. It dropped here in 2 days. Then they tested again in 8 days, and in some cases it went way up here, not too way up, but a little up. And in most cases, it just went back to normal. So let's say 2.2-ish in 8 days. So it went this way and then this way. So some koolbeens said, why is this, number one? And is this a transient damage to the immune system's function? And we are at risk during this time. So I wanted to share the mechanism of how this happens, and also within the study provide a verification as well. That study actually describes that too, what I'm going to show. So let's first look at the study. In the study, here is something that describes this. No clinically significant changes in routine clinical lab values occurred after BioNTech vaccination, in line with previous reports of RNA-based vaccines. A mild drop of blood lymphocyte counts without concomitant neutropenia and an increase in C-reactive protein were observed. So lymphocyte count went down, but neutropenia means neutrophil count, that did not go down, which is good, meaning it was not a pathology that brought down the neutrophils and lymphocytes. And these both were transient, dose dependent, and within or close to lab normal values. So the question is, why did it happen? So first takeaway, please keep in mind, it is within the lab's normal values. So let's say we draw somebody's blood and we put that blood, I'm making it a simplified diagram of this. So let's say we put their blood in here and we measure. In this blood, let's say these are the lymphocytes of the blood, all of them. And just like blood pressure can be 120, 80, and in some people it could be 122, and some people can be 110. There is a normal range, which means that in many people, the count will be found between this, let's say A, and this, let's say B. And if it is within this range, it is normal and it is fine. Now, it does not mean, so let's say these are all lymphocytes. So there's a count of lymphocytes that is present, and then I'm going to make it in blue just to say then there are lymphocytes that are here on top of this. If I can make a rough way of explaining it, let's say there are 1,000 lymphocytes present, and then there is another 10 that are in this fudge factor in the range. So this could be a person's lymphocytes could be 1,000 to 1,010. So if somebody's lymphocytes were 1,010 and then they became 1,000 and they are within the lab range, you'll say, yeah, sure, this is normal. It's okay. So that is one. The second question is, why did this happen? So what happens is, and for the medical professionals, I'm sure that you already know, and medical students, you will see that blood lymphocytes that are fighters for the immune system, you would see the things like marginalization of the lymphocytes and then extravasation or diapedesis and getting out of the blood vessels. These are normal processes. So I'm just going to explain that. So what happens is, imagine this is a, let's make it in red. Let's say this is a closed system, and maybe we should make a heart in here as well. Let's say this is closed cardiovascular system, and it has this heart in it, and then the blood vessels, blood is going and circulating. And there are, if you draw blood from it, you would see 1,000 to 1,010 lymphocytes per nanoliter. I'm making up a number to explain this. Now let's say here in some tissue, a war starts, inflammation starts. So what happens in the inflammation is, let's say the vaccine is injected, or let's say the actual COVID occurs, or some other infection occurs, or some other inflammation occurs, some autoimmune disease or something, and the inflammation starts. When the inflammation starts, the cells that are present and are resident in the tissue, for example, dendritic cells or macrophages, um, neutrophils, and others. So let's just focus on macrophages and dendritic cells. These cells will start the war. They'll start picking up the vaccine or the COVID, and they'll start creating inflammatory cytokines. When those cytokines are produced, in them there are chemokines as well. Every time I say chemokine, you should be recalling Dr. Bruce Patterson and Rantes and CCL4 and 5s. So chemokines are substances that are released in the area of inflammation, either by the activated immune system cells and or by the damaged cells and the debris that they release. Those chemical substances spread in the tissue, and of course, because there are blood vessels there as well, they enter blood vessels too. So now let's say there is a happy little lymphocyte, and it is going along its merry way. It is circulating and going everywhere in the blood system. And now in this round, when the heart pumped it and it took its little tour and it reached here, and I said, oh man, if I could make a cartoony sound here, it would, oh, I see these chemical substances. That means there's a war going on here. And these chemical substances, when they attach to this neutrophil, so let's say lymphocyte, so let's say this is a lymphocyte, and there are chemical substances. When they attach to it, then the microtubular system or the structure of the lymphocyte changes. It develops ways to bind to this area of the endothelial cells. Just like the marine planes that land on ships. So when they land on a ship, the ship has hooks to trap them. Otherwise, they could fall over from the other side. So similarly, when an area of the blood vessel is exposed to inflammation, that blood vessel cell will develop hooks on them. These are called cell adhesion molecules, CAMs, CAM, cell adhesion molecules. These are like little ropes that are put on the ship. So the lymphocyte or other cell that need to get out to help, they, when they are exposed to these chemicals, they also develop their cell adhesion molecules, and then these molecules, um, they kind of bind with each other. And it is so interesting, just like the real life, that when the plane is landing, it's not that it just lands on the strip and it just stops there. It lands and it starts applying the brakes and slowly becomes slow and then stops and then goes to the whatever terminal. Similarly, these little lymphocytes, so imagine this is blood vessel cells, they all have their little hands up. So this is a blood vessel. This is a war going on here, the tissue, and there are chemical substances. So the cells here, they have their hands up or their cell adhesion molecules up. And here comes a little lymphocyte, happy and dandy, and all of a sudden it saw these little adhesion molecule, plus there were these chemical substances. So it protruded its own molecule as well. And the first time it bound with the other molecule, it would not stop. It would kind of tumble across, still keep going because the blood is going fast. So it would still go forward and it would break off from this bond, but it would slow down. Then it would hold the hand of the next cell, and that would slow it down a little more, and it would go a little more near the blood vessel and it would slow down. So that is called marginalization. It is marginalizing, and then slowly it would start tumbling on these cells and slow down, and finally it would stop. How would it stop? Now the force of the bond is more than the blood's push or the velocity. And then it would drill a hole in the blood vessel and get out. This is the diapedesis, or the getting out of it. The point is, when from this blood system, you take a bunch of lymphocytes and put them out in the tissue, then if you measure the lymphocyte count in the blood, you would see them to be lower. Why they are lower? Because they are extravasating to the tissue where the fire is. So then the question is, can we make more and put them there? First of all, there is still a bunch of lymphocytes already present, so we are not at risk of anything. Secondly, our body takes a little time to start making more than the normal amount of blood lymphocytes. We are making lymphocytes and RBCs every single minute, but we'll have to kind of ramp up the production, and not only ramp up the production to go into the blood, we'll also ramp up the production for lymph nodes, and so they would start developing everywhere. So there would be a transient reduction in the blood, not in the body. These lymphocytes are actually where they should be. They have gone to the area of war, they're doing their war, and then you cannot count them in the blood with the same quantity. Then slowly these would start getting replenished, plus the cells that are present in the lymph node, they would start becoming proliferated, as I say that very often, and they would increase in number too. Some of them would go in the blood, some of them will be produced in the bone marrow, and so on. So then the system would start producing them. So now if I read this, both effects, that is the CRP change and the lymphocyte change, are considered pharmacodynamic markers for the mode of action of RNA vaccines. Blood lymphocyte counts transiently decrease as the lymphocyte redistribute in the lymphoid tissue in response to innate immune stimulation. So the these guys over here, these were macrophages, dendritic cell, part of the innate immune. So that is stimulating, that is sending these chemical substances, that is making these guys redistribute in this area. Yeah, sure. That's physiology 101. That is like first year, second year of medicine. Into lymphoid tissue in response to innate immune stimulation, and CRP is a downstream effect of innate immune modulation. And we know that once the innate immune system becomes activated, it would release, for example, interleukin 6, that would go to the liver, that would cause the liver to produce CRP, and so on. So it's okay that these things fluctuate. That is the normal behavior. We should be worried that the fluctuation did not occur. If you cause inflammation somewhere, and before inflammation and during the inflammation, the lymphocyte counts stayed the same, they didn't decrease and they didn't increase, that means the body is not responding. That is what should worry us, to say, what the heck, why is the body not responding? Okay, so that is one concept I wanted to discuss. I hope it makes sense. Then let me very quickly go over some more things. I wanted to make sure that these things are as valuable as they can be. This is